Hi, we're going to talk about matrix operations, and this material is at the beginning of Chapter 2. So the first thing we want to ask about is, when are matrices equal? So you might realize, in order for matrices to be equal, they have to be the same size, and each of the components have to be equal. So they have to be equal component-wise. So let's look at what are possibilities here. So if you look at this collection of matrices, A, E, and D are all 2 by 2 matrices, so there's some possibilities there. A and D, they agree on 3 of the components. A and D would be equal provided X is 3. So that's one possibility for matrices to be equal, in this collection. What else is a possibility? Well, if you look at A and B, A augmented with B looks like it would be, no, it doesn't. I take that back. A augmented with B does not look like F. E augmented with B looks like F, right? Because it's these 4 numbers with those 2 numbers looks like these numbers. So if you have E augmented with B, you get F. Those would be equal. That makes sense as well. What else? A augmented with B is G. Ah, that's what G is. G is A augmented with B, right there. So that makes sense as well. Now, if you think about the operation of transpose, the operation of transpose, that's an operation you can perform on matrices. I'm not sure if we spoke about that. I think we have not. So this is a little bit of a leap into the future. The transpose of a matrix is when you write a row as a column, or equivalently, if you write a column as a row. So if you take, like matrix A, for example, if you take this row and write it as a column, that would be the first column of matrix E. And if you take this second row of A and write it as a column, that's the second column of matrix E. So that operation is called transpose. We'll see it soon. And so A transpose is equal to the matrix E. Okay, so given that's the case, then we'll be able, since these three equivalences are written in terms of matrix A and E, we'll be able to rewrite those. Since A is equal to D, then that means E transpose would be equal to D, provided X is equal to 3. Since E augmented with B is F, that would mean A transpose augmented with B would be equal to F. And since A augmented with B is G, that would mean E transpose augmented with B is G. So you get all these things for free because, A transpose is E. And now if you look, I guess this is the thing that's the elephant in the room here. A and C, if you write this column as a row, then the relationship would be B transposes C. Okay, in terms of addition of matrices, this is very straightforward. If you have 2 matrices and they are the same size, then the operation of addition is defined, and the addition of the 2 matrices is defined component-wise. If the matrices are not the same sizes, then the operation of addition is not defined. Scalar multiplication, that is referring to taking a number, a real number in our case, and multiplying a matrix of any size. That's always defined. That's defined as the scalar times each of the components of the matrix. So here's a simple example of addition of matrices. Here's matrix A and B. They are 2 by 3 matrices, and if we look at the addition of these matrices, we will add these matrices component-wise. So the first entries of each of the matrices will be the first entry in the sum matrix. The entries in the second row first column, the sum of those entries will be the entry in the second row first column in the sum matrix, and so on. So the sum matrix will look like this. Matrix multiplication. You should take a look and read your textbook for a few pages where matrix multiplication is defined. We'll talk about it briefly here. So matrix multiplication is not always defined. The multiplication of matrices is defined provided they are conformable. So what would make matrices conformable? What would be needed is the number of columns in the left factor has to be equal to the number of rows in the right factor. So we can talk about A times B. A is the, I think I said the wrong thing. Oh, whoopsies. I think I said the wrong thing, but I don't want to redo this video. I said A is a right factor, but indeed A is a left factor, so I apologize for that. Here's the product matrix. A is the left factor, B is the right factor. If the number of columns in the left factor is equal to the number of rows in the right factor, then the matrices will be conformable and the product will be defined. In the size of the product matrix will be M by P. The product matrix will have entries, and those entries will just be, well, not just, those entries are given by what's called a scalar product. So the ijth entry in the product matrix will be given by the product of the ith row in the A matrix times the bth column, or the jth column of the bth matrix, the B matrix rather. Okay, so the ith row of A times the jth column of B, this sum, which is called an inner product or a scalar product, that will give the ijth entry in the product matrix. So a nice picture of that is here. So let's take a look. So here's A. A is the left factor. Here's the matrix B, that's the right factor. And, this is done in the abstract, so, we don't have numbers here, but we have these letters representing the entries in the matrix. And so because the number of columns of A and the number of rows of B, since those are the same, the product is defined. So, these are conformable matrices. The product is defined. And so, what is the product matrix? Well, we can look at the entry of, say, two entries in the product matrix. This first entry in the product matrix, which is indicated by C11, that C11, where does that come from? Well, the way matrix multiplication is defined, we'll take the first column in the B matrix and multiply each of the rows in the A matrix. And as we multiply each of the rows in the A matrix, that will give the first column, whoopsies, let me go back. That will give the first column in the product matrix. So again, take the first column of B, multiply the first row of A, that will, by using scalar product, that will give the first entry here. Multiply the second row by the first column, that will give the second entry of the first column. Multiply the ith row by the first column, that will give the ith row in the first column. Multiply the last row by the first column, that will give the last row in first column in the product matrix. And when we do this multiplication, again, that multiplication is defined by, whoopsies, where is it? This scalar product. Okay, it's the scalar product. Okay, so that's how we got the first column in the product matrix. How do we get the jth column in the product matrix? To get the jth column in the product matrix, we're taking the j column of B. The j column of B times the first row of A will give the first entry in the jth column. The second row of A times the jth column of B will give the second entry. It's not written here in the abstract, but it would give the second entry in the jth column. The ith row of A times the jth column of B gives, in terms of scalar product again, that gives the ijth entry here. The last row of A, row M, times the jth column of B, using scalar product, would give this last row in column J. So that's how matrix multiplication is defined. So let's look at an example, or a few examples. In this first example, we have a product of two matrices. This first matrix has 1 row, 3 columns. This matrix has 3 rows, 1 column. So if you take a 1 by 3 times a 3 by 1, you can see 3 columns in A, 3 rows in B. These matrices are conformable. The product is defined. And so the result would be just what's, the scalar product. We'll take the first entry here times the first entry here, plus the second entry here, plus last entry here, last entry here. You end up with 1. What you have in your notes is the R code for this, and I'll do that in a moment. Okay, so let's look at the next set of matrices. This matrix is a 2 by 3, 2 rows, 3 columns. This matrix is a 3 by 2, 3 rows, 2 columns. So 2 by 3 matrix times a 3 by 2 matrix. These are conformable because the number of columns in the first matrix is equal to the number of rows in the second matrix. So the result here will be a 2 by 2 matrix. So how will we get the 2 by 2 matrix? Well, the first entry in the 2 by 2 matrix will be the scalar product of the first row times the first column. And the second entry, and by second entry I mean in the second row, first column, that would be this column times the second row using scalar product. So I have that written out here. So let's look. First row, first column, that scalar product is here. Second row, first column, that scalar product is here. Now for the second column of the product matrix, first row, second column, that scalar product is here. Second row, second column, that scalar product is here. So the result is, this 2 by 2 matrix. And again, the R code is in your notes. I guess it's time to look at that now. So if you have R installed, to define a matrix, I'm first going to use a temporary variable, and I use this function C, which stands for catenate actually. So we're going to concatenate together this array of numbers, and then I define, I'll let capital A, it'll be the name of my matrix. Capital A will be, we'll define that as a matrix. I'll use the temporary variable temp. I'll have 1 row, 3 columns, and I'm filling the matrix by row. So if I enter that and I look at capital A, because R is case sensitive, capital A is not the same as little a, you can see it's what we want it to be. It's 1, -2, 3. And so I'm going to play the same game with matrix B. Now for matrix B, the array of numbers I want is 2, -1, 1, right? 2, -1, 1. So I'll store that, I'll concatenate, use this concatenate function and store that in this temporary variable temp. And then I'll define my matrix B. It's matrix. Matrix is a function. Matrix, I'm using the temp variable, 3 rows, 1 column. I'm not going to put by row equal to true because I'm filling by column. So if I execute that command and look at B, it's what I want it to be. So we already know these are conformable, so we can look at the matrix product. Now matrix product in R is, oh whoopsies, I did not mean to do that. Matrix product in R is uses a kind of funky notation in standard R. It's the left matrix, and then you need percent symbol, multiply, percent symbol, and then right matrix. So it's really you need 3 characters for matrix multiply in standard R. So if you do that, then you can see the result here is going to be 1. Yeah, and actually, I just mentioned this now. If you're interested in what the C function does, if you just did, you know, what is that called? Question mark C. You know, it will pull up your browser because C is a, you know, is a function, and you'll get the R help. And it might take a moment. So objects to be concatenated, so that's how we were using it. So we were using this C function. And so we'll, you know, the help in R, you can get help just with the question mark. Okay. This next case that we had done, this product of these matrices, I'll play the same game. So if we look, the matrix A, I'm going to concatenate. I'm filling by rows. It's this array of numbers, right? 103, 2, -1, 2. So that's the first matrix. I'm defining that as A. I'm using the matrix function, which takes anything in this variable and will make it into 2 rows, 3 columns. This is the syntax of the matrix function. So it takes the contents of this variable. This is the number of rows. This is the number of columns. By row equal to true because I'm filling by row. I'm going to refill this dummy variable. Now I'm going to concatenate the next array of numbers. And here I'm filling, you know, by column. So, and that's the default for R. So -2, 1, -1, 401. So -2, 1, -1, 401. These need to be separated by commas. And now this will be called B. So B gets assigned matrix The temporary variable is called temp. This is 3 rows, 2 columns. So when I execute that command, if I look at A looks the way it's supposed to look. Look at B looks the way it's supposed to look. If I look at little b is not found because, again, R is case sensitive. Little b is not defined. I never defined it. I only defined a capital B. And if we want to do the matrix multiplication, we need the percent multiply percent. So the matrix multiplication is what we got before. Okay, so here we have 2 matrices. This is a 2 by 3. This is also a 2 by 3. And we need to do a little bit of arithmetic. So first thing would be to define these matrices. And hopefully you know how to do that already. The code to do that is in your notes. And so let's make sure we did that correctly. So if you look at A, that is what it's supposed to be. Look at B. B is what it's supposed to be. And so if we take A and multiply by B, you get an error. They're not conformable. So I guess that makes sense because A is 2 by 3, B is also 2 by 3, so the number of columns of A is not equal to the number of rows of B. These are not conformable matrices. Multiplication is not defined, so you do get an error message here. But these other operations are defined. So like addition, for example, is defined because they're the same size, so you can multiply them. Excuse me, I said multiply, but I meant add. You can add those. They will add component-wise. You can subtract those, and they subtract component-wise. Scalar multiplication, so 2 times A multiplies every entry of A by 2, and then this last little operation, 2 times A minus B, should be, very straightforward.